Hey all, it's Andrew Couch here, and in this Tidy Tuesday video, I'm going to be going over the included plotting functions in TidyModels. What's really great about the TidyModels package is that it basically has everything you need when you want to do some type of machine learning, and it includes some pretty nice plots to use when you want to do some model diagnostics. So I'm just going to go over a basic modeling workflow. I've already coded everything out and I've actually ran the script already. So that way we don't have to really wait for any like run times or rendering. We already have the objects created. And I'm just going to show you just some ways to plot out or to use the actual plotting functions that are included inside TidyModels. So I'm going to walk through basically each code chunk, and then we're actually going to see the plots, and I'm going to kind of explain what each plot does and how you can use it in your own analysis. So obviously the first package we're going to be using is the tidy models. We're also going to use stacks because I've noticed that a lot of people want to do a lot of like ensemble stacked machine learning models. We're going to use fine tune, which is also a different way we can tune our models. The VIP package, which is used for variable importance scores. Um, we're also going to use tidy posterior, which is good for comparing different models, and also model data, which is a data package that's included with the tidy models package. I also have the option set to tidymodels.dark. That's mostly for the fine-tune package, but that's not really necessary for this actual process. So I decided to actually do two different data sets, a regression and classification data set. So that's why I call in the two class data. It's just a simple binary classification data set. What's interesting about it is that there's really nothing to kind of extract out of it. Just two features, A and B, and the class. So this is mostly like kind of like a simulator, a simulated data set to use for like analyzing different model algorithms. And we're also going to use the Ames housing dataset as our regression dataset. So classification data, we're just trying to classify class. There's no real background information for what it is. And then the regression dataset is the Ames housing dataset, where we're going to be predicting the sale price of the house. Since this is included with the model data package, I wanted to do some checks just to see if there are any missing values. So in this case, we don't really have to do anything because it's included into this package. And that what they want to basically have you guys do with these data sets is kind of just to test out and learn the tidy models function. So pretty clean data set to actually work with. So I create some basic data partitioning, using initial split. For the classification data set, I stratify based on class. Again, this isn't completely necessary just because like this is a simulated data set. So we don't really know what we're actually trying to do with it. It's just a good thing for, I guess, a nice example. Create the train data sets to be used in a pre-processing. And then we also create our k-folds cross-validation sets with the existing train samples. So for the actual pre-processing, the class recipe for the classification data, there's no real pre-processing because there's only two features, and we're trying to predict a binary outcome. So in this case, it's just a simple formula, which is not really something that you'd actually be doing in your own workflows. You probably have to do some type of feature engineering. But for this example, let's keep it a little bit simple. For these other two recipes for the regression problems, I wanted to basically do your typical pre-processing. So with the Ames housing data set, we actually have a decent amount of columns. So I wanted to basically remove any columns that have near zero variance, any correlated features. We do some normalization, some box Cox transformations. We do some lumping in the categorical variables, and then we dummy them out. I wanted to make another recipe or another pre-processing object, where in this case, in case you want to actually tune a recipe, which is definitely something you do a lot when you're doing your feature engineering, is in this case, it's mostly tuning how many things we want to remove. So in this case, with near zero variance, I tune the two parameters to basically decide what type of columns we want to keep, and also the threshold for the correlated variables. So we'll see that basically in the other plots below. As for the actual models, I created three different models for both the classification and regression problems. This is what I usually start out with, anyways. I usually do an elastic model, what's called like an elastic net model. So generally, just tune the mixture and penalty parameter, XGBoost model, and a random forest model. For XGBoost, I usually tune a little bit more parameters, but in this case, I want to just tune learn rate, number of trees. I will often tune the tree depth, but again, this is just an example. I don't really care about predictive power that much. I just want to use it to get some plots. And then finally, we do the random forest model. In this case, I just want to plot the or tune the number of trees, so nothing too crazy over there. One thing you might notice is that the XGBoost random forest models, the only thing that changes is the mode, right? But for the elastic models, you need to specify linear or logistic regression for the um, uh, for the classification. And I actually need to change these things. Classification, cool. Okay, so for the actual metrics, I'm gonna do your typical predictive modeling metrics. So classification, ROC, AOC, and accuracy. Regression, root mean squared error, mean absolute error, and R squared. And also set up a model control because I'm going to do some stacking for the models because I obviously with slice going on, people are really getting into these ensembled models or stacked models. So I figured I'd show you a nice plot that you can use when you're doing your model stacking. Usually these parameters or these metrics are included inside of your tuning process. However, when you're using the fine-tune package, you kind of need to specify the parameters you want to optimize based off of. So in this case, you have to show your first parameter as the thing that fine-tune will choose. So in this case, we want to prioritize ROC, AOC, and for our regression problems, we want to prioritize root mean squared error. Okay. I also experimented with this other package, which is, I think, a little bit newer, which is workflow sets. I think this is actually a really good package. The only thing I wish they had was a model control process. So that way, if you're going to tune a lot of models, you might want to save the predictions. So with classification set, in this case, I didn't really feel like saving the predictions. I just want to show an example in case you're actually doing with workflow sets, the included plots that are with it. But it's essentially doing the same thing that I've always done, which you create a list of recipes that you want to use for all the models, a list of all the models that you want to tune, and then you basically specify cross or crossing. Basically compute every pair of recipes and models together. You can also do an anti-join, so you can remove redundant pre-processing model pairs. So like if you have some type of normalization process, it's not necessary for tree-based models and stuff like that. So you can do that. But again, let's keep it simple. And in this case, instead of giving it a grid, because you might notice that I don't use any grids, or I don't create any grids for the actual models. I use tune for using simulated annealing. So that'll basically tune it for me. Um, and then I also tune the models with different methods. So with the classification, I wanted to show you how you can use workflow sets and use tune it with simulated annealing. With the elastic model, I wanted to show like an ANOVA tuning procedure, and also a Bayesian procedure. So these tune in different ways. And then I also did some basic tuning with the traditional where you just give it a grid. When you use tune grid, you can either give it a grid or it'll just automatically tune with a predefined grid that they just kind of include with the models. So I just left it like that. And then finally, we actually have the results. For me, I just like combined all of the models into a single tibble or data frame. And then I basically extracted the top root mean squared error from each model. And you can see that, what we would expect, XGBoost performs better, Random Forest performs pretty good, and Elastic model performs a little bit worse than those nonlinear models, which is not, surprising at all. Okay, so now we're actually go into the actual plotting. So this is the workflow set, or where we basically tuned all of the model and recipe pairings. So if I do that with the auto plot, we can actually get a pretty nice plot right here, where it's just showing, each rank of the models, because you have to realize that we're using different parameters for the models, but we can kind of see that, logistic regression or our elastic model has the higher accuracy and also higher ROC AOC scores, and you can kind of see it kind of drop off. One thing that's pretty interesting is we can see like a definitive like kind of a grouping where they're obviously not this very similar. I think the logistic regression model is definitely the best. So that's a pretty nice, handy way to basically extract everything we really want out of these workflow sets and get like a high level overview before we start looking at the actual models parameters. So I rank the results so we can kind of get a nice little um, thing for it. So we can see that, yep, our regular elastic model is the best, pretty high rank. And we can see that ROC AOC scores are pretty stable. Okay. One of the things I also want to do is kind of just compare these two models. So I figured, we'll just extract the best parameters for both the elastic and random forest model, and we'll tune it later to basically use the tidy posterior package to basically compare the models. So that's just me grabbing them out so I can hard code them out. Now we can go back towards our other tuning procedures. So this model or this tune grid is your typical tune grid where you give it a grid or you give it a grid length and it tunes the model. And what's nice about it is we have a nice little autoplot function where we can see, let me actually go back here, where we can see kind of like a faceted chart of all of the parameters and kind of its relationship with our metrics that we want to analyze. So let's kind of go one by one. I think obviously we want to probably look at root mean squared error, but realistically, root mean squared error and mean absolute error are going to be correlated together. So with the number of trees, we can kind of see it's a little bit all over the place. Unique values and frequency distribution ratio, again, is with kind of all over the place. But the big thing we can see is the threshold, right? So right now we can see how when we increase the threshold, we can see our root mean squared error has been decreasing. So there seems to be a lot of noise within our features. So when we think about it, we might want to go back and do a little bit more feature elimination and in our recipes and start tuning more models. Cool. Um, right now I'm going to also show you the nice little plotting function using the was it the I think this is the this is the race and nova. So instead of using so we're using tune race and nova, which uses the nova scores. And we can see this how the race generally you can see a little bit more separability between the lines, but we can see that how it's the tuning function has gone on through it. Again, this for the race and nova, it's not as interesting, but it still might be useful for other model analysis. If you see some jagged lines between each of the lines, you might have to consider that your k-fold cross validation set is running into problems. Okay, so this is the tune base. So instead of using the race and nova or the regular grid, I'm using some Bayesian analysis, where it's basically kind of going through iterations and saying like how much of an expected increase in performance I think. So we can see the iterations and where it's going. Go here and we see how the more iterations it's kind of it's decreasing our mean absolute error, root mean squared error. So we might want to consider running with more iterations. What's nice about the Autoplot is there are different commands, mostly with very specific things. So with performance, you need to have some type of iterative process for your tuning grid. But if you do parameters, again, this is the same thing as our regular Autoplot with our regular tune grids. So again, if we reload it, yep, we can see again the threshold makes sense. Proportional lasso thing kind of makes sense. There probably is some interactions between the lasso penalty and regularization. So yeah, again, pretty interesting. And then lastly, let's go to marginals. Right there. Oops. So yeah, you can see that again. not too interesting, but there's different ways to basically view your own tuning results. Okay, so I think this is a pretty interesting way to do it, and I also think most time you should be looking at these types of plots, just how your parameters, the overall trend of your parameters are going, so that way you can kind of keep on tuning your model, or at least like tune uh, specific parameters in a more informed manner instead of just tuning it all uh, using just like the pairwise, or using the crossing function to get all the combinations. So I wanted to also do some more classification plots. So with the classification plots, I needed to basically refit the two models so that I could compare them together, and also so I could create the classification plots using the confusion matrices and stuff like that. With tune simulated annealing, there's no way to specify the control, at least with workflow sets. So I just refit some models using k-folds cross validation right here. So I just fit the resamples, and then I specify the control, which is save pred equals true, or save predictions equals true. Um, so I want to show you a few things. Maybe do I? Okay, a few things. So once we have these things, once we have our predictions from our plots, we can collect our predictions, right? So when we collect our predictions, we can get the IDs of the folds. So each fold, the predictions, the probability of that class predictions, and stuff like that. And we can create a few different plots. So the first plot I think we can do are your general curves. So like a gain curve, ROC curve, and a lift curve. In this case, you just use the functions. Truth equals the outcome of the class that's actually true. Estimate is the probability. Um, and then you just do autoplot. So again, that's pretty cool. You can also do like lift curves too, and precision recall curves. I just wanted to do, I guess, curves that I think are more useful. So gain curve, again, pretty good. It's like the milk skimming thing where you do like the top percentage of top most probable predictions, and then you extract the percentage found. Your typical ROC curve, just how well um, your model is doing in predictive power. And then you have lift curves. I'm not really someone who uses a lot of lift curves, but I wanted to kind of demonstrate how you can collect the predictions and do summarize equals false. Um, and that way we can actually group by ID. I don't think you actually need to do summarize equals false. Uh, you can group by the actual ID or the folds, and then do the lift curve, and then autoplot it. And autoplot is smart enough to understand that since we have these IDs, they'll plot each ID's lift curve. So that might be good when you want to like kind of assess model stability and stuff like that. So maybe it's not great for lift curves, but for like ROC curves, it's probably pretty useful. So like maybe you can just do that right now, just to show you guys. Group by ID, right? And we can see, there's some folds that we do really good on, and some folds that we don't do great on, which makes sense. And I guess I forgot to do a confusion matrix one, so I'll just do that right now. With the confusion matrix, I think it's a little bit odd. So if you must filter the ID, so fold equals 0, 1, and then you can do a conf mat, and then oops, and then you do a conf mat class, or was it truth is equal to class estimate equals dot pred class, and then you can do an auto plot. So the first one is the like mosaic, which I'm not really a fan of, but you can also do like I think a heat map, and then you can kind of see your typical confusion matrix. So again, I don't really like it too much. I also run into some problems with wanting to do confusion matrix resampled. So if I do this, say conf mat resampled, it won't do it. So maybe I can just, yeah. So I don't know why it does this sometimes, but I just couldn't get it to work. Let me just see if I can just do it one more time. Truth equals class estimate equals dot pred class. Yeah. So maybe I can one more try. yeah, so we do that. And then even when you do an autoplot, it doesn't work because it's not supported. So kind of weird, but um, weirdly doesn't work. Okay. Well, for some reason, complement resampled, or basically taking the average of all 10 confusion matrices from your k-fold cross validation sets, doesn't work with autoplot, but they give you a nice little thing where it's a simple GM tile with the GM label. But again, I'm not gonna really sleep over that. So I think with your typical modeling workflow, you kind of view your curves. You send it over to your marketing team or sales team or whatever, for a presentation, and then you kind of have to decide, hey, what if you have these two models who um, are very similar in predictive power? So in this case, I guess we'll just say our elastic model and our random forest model. um, how should we how should we really choose these in between these models? We'll just join them up together, and we'll use the perf mod from the tidy posterior package, and that'll basically give us a nice little comparison. What's nice is you can just do a simple auto plot and kind of see the distribution of um, the scores, and then we can also do a difference, so we can see like what's the difference between our elastic models ROC AOC performance with the random forest, and then we can kind of get the actual probabilities of it being better, which is pretty useful. But just using basic intuition, we know that elastic models are simpler than random forest models. It has significantly better performance, in my opinion. So we would just choose the elastic model. But pretty nice plots to create. Very quick way to actually analyze your models and try to decide which type of model you want to use in your final decision. So now we can actually go to model stacking. In this case, I just wanted to combine these tune results from our random forest model and our XGBoost model. That kind of makes sense, at least from like a Kaggle style competition. If we note, we can see our control that I've put in when I was tuning these models was model control, and model control is a control stack grid. So that's why I'm able to use these tuning results inside a stack. So maybe if you don't really want to choose a model, you just want to combine them together and create a final model for like a Kaggle competition. We'll just add the candidates, blend the predictions, and then we can kind of analyze our actual ensemble model. So we can get some nice little diagnostics on like number of members and the average. So we can see how it's changing with our penalty because we're tuning essentially I think Elastic model, or at least an Elastic net model, onto our stack. So we can see how our penalty has influenced the results from our model, our stacked model. Again, what's nice about Autoplot, we have different types. So in this case, it doesn't really matter that this one doesn't really matter that much. So I don't really need that. I think the one that's the most useful is the weights. So if you say type equals weights for an Autoplot with a stacked model, we can see that our boosted tree, it has the most, it has the highest weight. So it's the one that we want to, it's going to use the most, which is pretty nice. We're actually using a variety of different, I guess, XGBoost and random forest models, but we can see that XGBoost model has the best performance and weight. So that's one other way we can actually do some decision making when we're comparing models, is we can kind of set up essentially a stacked model. Even though if we don't really care about the stacked model, we can use these essential model weights as a way to decide what type of model, which model is the best model. Right. So that's a thing you commonly see in the BRMS package, for example. And I think if we look at it, we can see obviously XGBoost has the better performance from root mean squared error estimate. So if we're gonna do that, maybe we also want to see some variable importance scores. So we know that, hey, our XGBoost model is great at predicting sale price of a house. Let's extract the one with best root mean squared error, and then let's actually find like the actual variable importance to figure out why it's thinking that. So I just created a simple workflow, combined it, added a XGBoost model that has no tuning parameters, the recipe that was for it, and then we just select the best XGBoost model that was using the regular recipe. And we want to choose the one with the best root mean squared error. Um, then we fit it to the actual data. We pull the actual model fit object, and then we just put it back into the VIP package. And then we can see our variable importance scores, where I can see like, hey, we think the garage cars is one of the most important aspect of the actual model when predicting sale price. I think this is something great, whether it's like a great living area, total basement, how young was the house, year it was remodeled, fireplaces, second floor, first floor, square footage. So again, all this stuff makes sense, right? Number of if you think about it also, it's probably pretty related to each other. Like if a house has a ton of space for cars, it probably has a pretty big square footage, right? Pretty big lot area. So yeah, that makes sense. And we can also do the VI function, which will kind of show it in the positive and negative. So what contributes to a huge decrease in value and what contributes to a huge increase in value, but it won't actually show the the score of it. So yeah. I know this was a pretty quick video, and also it was pretty simple because there was pretty minimal code, but I think this is a pretty good script to kind of look at and kind of see how TidyModels works and how all the plotting functions work. So that way we can kind of minimize redundant plotting code in our um, like our markdown documents and stuff like that. That being said, there's always a need to make your own custom plots, and that's why I'm going to make a video soon going over all about the grammar of graphics with ggplot2. So I'm pretty excited for that video, and I'll record it and post it after this video. So I'll see you guys next time, and tidy on.